Okay, so here's some basics on torque. Oftentimes you'll have a steel beam or a similar beam attached to a wall, and this symbol here just means that it's a rigid wall. It's fixed. It's not going anywhere. Okay, and for this we're going to be working with rotational axis number 1, but you could just as easily work with this spot here and use that as your rotational axis, and I just labeled it number 2. You can frankly create a rotational axis anywhere along here. It just works easier if you have a point where you can actually cancel out some forces, which this would be a place where you could cancel forces. Any place where the forces are on the beam, where you can find the point of the force, like here. Any of these places would be good to create the rotational axis that you're going to work with. And when I say rotational axis, this whole object here, this whole beam, everything here is not moving. It's a static system, and so you can create a rotational axis, so to speak, anywhere in here, because you're just going to be summing up your torques. They're going to be equal to 0 because it's not going anywhere, and so you can do it. You can place your rotational axis, and by that I mean that's the reference, the point of reference that we're going to use for this. You could just as easily put it here. You could put it here. It's your choice. It's smart though to pick a rotational axis where you're going to cancel out forces, particularly here and here, and this would be a good place too, because you can knock out 3 forces right here, and you'll understand what I mean in just a moment. Okay, now here's the free body, if you will. I've removed the wall, and all free body means is you've taken away everything that's causing the forces so that you can analyze the body better. And so what I've done is here are the forces due to the rigid wall. I've just labeled them W's for wall, and that's X direction, Y direction. And then this is the force due to the mass that was hanging here that we had right here. And then this mass 2 is the mass of the beam. It's just this. I'm considering this to be the center of mass of this beam, including this part here. Originally I hadn't drawn this here, but I thought I would add it so that I could explain some other stuff. But we're considering this to be the center of mass here, the center of gravity. And so that's where that force is pulling from. And then these are applied forces here, applied force 1, 2, and 3, because I wanted to convey some more information with that. And then here's the tension force from this cable here. Okay. Now, I went ahead and broke up the tension force into its X and Y components, if you will. Here's the Y, and then there's the X. Likewise, I kind of put in some dotted lines here. There's your X component and your Y component, because we need to have perpendicular forces to work with, because when you're working with torque, you're working with the force and where it's perpendicular to the distance from the rotational axis, and in this case, this is where we're working from on this one. I've also given labeled distances on here that are the perpendicular distances. All right, so the force of mass 1, this is the distance from the rotational axis, and that is the perpendicular distance. Okay. All right. Again, for the mass of the beam, this is the perpendicular distance, because we're assuming all the mass of that beam is being centralized at this point here. Okay, and so this is the perpendicular distance for this force here, and this is the perpendicular distance here, just to take you out to the edge of the beam. So if you wanted to apply some forces there, that would give you that distance. This distance here is for this applied force A2. Frankly, excuse me, it's for all of these, any of these forces that this is a perpendicular distance for. All right, so now we're going to sum up our torques. And one thing to keep in mind, in this instance, I'm going to say that clockwise is positive, counterclockwise is negative. And the sum of those is going to be equal to 0. And to get your torque, you multiply the perpendicular force times the distance from the rotational axis or from the fulcrum, the point that it's rotating around. And it's going to be in Newton meters if you're using metric. Okay, bear with me. Okay, and so here I'm actually showing the equation for this. So here, this is, and tau is the symbol for torque, and this is the sum of the torques around rotational axis 1. Again, clockwise is positive. And if you'll look here, all right, so this is the force due to the wall in the x direction and the y direction. Look, I've got zeros in here. So see, because we're at rotational axis 1, remember what I said? That gives us an advantage, because forces x and y are 0 distance from the rotational axis 1, and so there's no leverage, there's no lever there, there's no moment arm. Okay, so it's 0, and so that means, and this is one of the advantages of picking a reference spot near some forces. So see, these two we don't have to consider because they would be multiplying against 0. It'd be like pushing against the hinge of a door. It wouldn't go anywhere. Okay, so next we've got the force due to mass 1, and it's distance. All right, we're showing x1, and so there's the force due to the m1, and there's that perpendicular distance there. So that's the torque, and that is going in the clockwise direction, so it's positive. Okay, so that's why that's positive there. And next is the force of the mass of the beam, and we're multiplying that against x4, which is this distance here. So that's the perpendicular distance for that one. So from it's pulling that distance on this beam here, and that's the torque it's creating. Okay, and the next one is the applied force 1. Remember, that was right here, and its perpendicular distance is going to be x6. And let's see what we've drawn in here for that. Okay, so for the applied force 1, even though you've got this distance here, that doesn't matter. You're looking for the perpendicular distance from the rotational axis, and so this distance here, this x6, is the actual perpendicular distance with reference to this rotational axis here. And I'll explain more how that operates, because you would think that this distance here would also be included, but it's just this perpendicular distance here. And I'll explain that better in just a minute. Okay, so that was applied force 1, and then we're going to go to applied force 2. Again, all these are going in the counterclockwise direction. So see, these are going that way. And and so applied force 2, its distance is going to be x5. All right, and so it's pointing up in this direction, FA2, and its perpendicular distance is this x5. So that distance there. It doesn't matter what the length of this beam is. It just matters, this is the perpendicular distance for this applied force A2. Okay, and then let's go back to the equation here. All right, so then FA3, we have to break up into its x and y components. And so we've got that here and here. In this case, the x component is going to be the cosine, the y component is going to be the sine. Sometimes it can be reversed depending on what your reference angle is. Okay? And so again, these are going in counterclockwise directions. And so applied force at 3, cosine of beta times x6. And again, so FA3 with the cosine is this force right here. And so its perpendicular distance is the length of this beam here. It has nothing to do with this distance here. Okay? All right, next is FA3 sine of beta, and that's the y direction. All right, and so that is this part right here. This is sine of theta, and so it's not actually out here. It's actually going through the center of this beam, and I'll show you that in a minute. So its distance, its perpendicular distance, is going to be this x of 5. Okay. All right, and then now we're going to go to the tension, or the cable that was pulling this thing, and so the first one on there in the y direction is the tension, or T, times sine theta times x2. All right, so let's see, where's our x2? Here we go. So there's x2 there. That's the perpendicular moment arm, or perpendicular distance for this T force here against sine theta. Okay, so it's going to be pushing that distance from the rotational axis over here. All right, so that's how we figure out that torque. And then the last one is T cosine theta. And we have a special surprise here. Okay, because see, this is not actually where it's located. I just drew it out there so I could show the x component of that. And its moment arm is actually pulling from the center here, so it's actually pushing into that rotational axis, and so the perpendicular distance is actually 0, and I'll be showing you that better in just a moment. Okay, now let me get positioned here for this one. All right, so I'm going to show the angled forces. So we had an angled force there, and we had an angled force there. Right, so I'm going to separate. I'm just going to show them individually. Now, the point that this force is pulling from is this point right here, and so that's actually where the x and y components will pull from, if you will. So I've shown them here in dotted lines here. So that's your y component, and that's your x component. Sine of beta is the y, cosine beta is the x. All right, so see here, this perpendicular distance here is what FA3 sine beta is pushing against. Okay, so that's the lever arm for that force. So I just wanted to kind of give you a better illustration here, because it's actually pulling from that point there. And then the one in the x direction is pulling out this way. Now it's actually, its lever arm is going to be this piece right here. And now because it's away from this arm here, it's going to use that's the perpendicular distance for that force. All right, let me show you the next one. Okay, again here, this tension is actually coming from the middle of the beam, and so the x and y components. The x component is going to be going right down the beam. It's pointing at the rotational axis. So that's why there's no leverage arm, there's no moment arm that it's pushing against. So the distance, its perpendicular distance, is 0, and so that's why that one cancels out. And so then this is the tension times sine theta, and that's our y component, and this is the lever arm, the perpendicular distance for T sine theta. Now I just wanted you to see that they're actually coming out of the center of this beam. They're not actually up here. That was just to break them up in their x and y components. But hopefully that helps to explain some of this, and as you have questions, let me know if this helps.